Fatigue. So this is a form of failure when the structures, they are subjected to dynamic and fluctuating stresses. So under these circumstances, even though the stress is much lower than the tensile and yield stress with respect to monotonic loading, the material is subjected to failure because of the fluctuations in the stress, because of the cyclic loading. Some of the components that are subjected to this type of fatigue failure due to fluctuations in the stresses are bridges, railroad components, and machine components. So this fatigue, it was first recognized in the early 18th century, where most of the railroad components and bridges are subjected to failure due to repeated stresses. As time progressed, there were demands for the new materials for number of applications. So this fatigue also increased in most of the materials. The form of failure, that is fatigue, is also be seen in most of the components, most of the structures, due to repeated or due to fluctuations in the stresses. So early contributions of this fatigue was done by August Wöhler, W-H-O-L-E-R, August Wöhler. This fatigue, this is the form of failure, it does not occur suddenly, but it occurs over a lengthy period of time when the component or the structure, it is subjected to repeated cyclic stress or cyclic strain. So this fatigue is catastrophic in nature. It occurs suddenly without warning, but it takes a very lengthy period of time for failure to occur, even though the stresses are well below the tensile and yield stress of the material. Tensile and yield stress with respect to the monotonic stress or the static stress or the static load. So most of the metal failures are due to fatigue, and with respect to the investigations made, it was assumed that approximately about 90% for the cause of failure is due to fatigue. Fatigue is seen in metals, ceramics, and polymers except glasses. So most of the automobiles on road, ships at sea, turbines, all these, airplane wings, all these are subjected to fluctuations in the stress, cycling of stress and strain, and they are subjected to failure by means of fatigue. So this fatigue can be defined as the progressive accumulation of damage due to fluctuation stresses. Damage is accumulated due to fluctuations in the stress, and finally the component fails. So fluctuating stress, it is made up of two components. The fluctuating stress is made up of two components. One is steady stress or the mean stress. It is made up of two components, that is steady stress or the mean stress, and sigma A, which is a variable stress or alternating stress. Steady stress or mean stress. So the main basic factors that leads to fatigue failures are three types of factors. The first factor is large magnitude of tensile stress. Then the second factor that contributes to fatigue failure is a large fluctuations or large variations in the stress. large fluctuations or variations in stress, then a large number of cycles. So the three basic factors that contribute to fatigue failure are large magnitude of tensile stress. That means the net stress, it should be tensile for the crack propagation to take place and finally leads to failure. And there should be fluctuations in the stress. Fluctuations in the stress, mainly it contributes to the initiation of crack. So this is to initiate a crack, and large magnitude of tensile stress to propagate a crack, and then number of cycles where the material undergoes final fracture. So all these three factors contribute to fatigue failures which propagate crack. So net tensile stress is required to initiate crack. Large fluctuations are required. So these are the three main basic factors that causes fatigue failure. Now there are various stress versus cycles. That means various forms of stress cycles. Among the various forms, the three most common forms of stress versus cycles are: the first one is reversed stress cycle, second is repeated stress cycle, and third is random or irregular stress cycle. Now we shall see what is reversed stress, repeated stress, and random stress. The reverse stress cycle is where both the maximum and minimum, the magnitude of maximum stress sigma max and the magnitude of minimum stress are both equal. This is 0, and positive stresses are tensile and negative stresses are considered as compression. So the component is subjected to repeated tensile and compression, but the magnitude is same. Sigma maximum stress, the magnitude is equal to the minimum stress, but one is tensile, the another is compressive. So this is known as reversed stress cycle. So this is stress on y-axis and cycles on x-axis. So this is known as reverse stress cycle. The second type of stress cycle is stress versus cycles is repeated, where stresses are positive, stresses are greater than 0. That means they are only tensile, but the maximum value of stress is not equal to the minimum value of stress. There is a difference in the maximum and minimum value, but both the stresses are tensile. It can be compressive also. So this is the figure which shows the repeated stress cycle, where sigma maximum and sigma minimum are both tensile, but there is a difference in the value, difference in the magnitude. This is sigma minimum and this is sigma maximum. This is sigma maximum and this is sigma minimum. This is the second type of stress cycle, that is repeated stress cycle. Then the third type of stress cycle is known as random or irregular, which is especially encountered in the case of airplane wings. So this is stress versus cycle for the case of random or irregular stress cycle. So these are the three common forms of stress cycle: reversed stress cycle, repeated stress cycle, and random or irregular stress cycle. Initially the origin of the fatigue test was conducted by R.R. Morey testing machine, rotating bend testing machine, which uses this type of stress cycle, that is completely reversed stress cycle. So most of the literature, it has the data with respect to this type of stress cycle, that is reversed stress cycle. So the first fatigue equipment is based on the reverse stress cycle, that is R.R. Morey reversed bending machine, which conducts the fatigue experiment under completely reversed stress cycle. Later on, the modern machines, which are based upon closed loop servo hydraulically controlled machines. So with the use of these machines, there is a flexibility in the parameters as well as with respect to the design of the fatigue specimens. There is a lot of flexibility in those modern machines, which are servo hydraulically closed loop controlled machines. And whereas the first machine is R.R. Morey reverse bending machine. Now from this different stress cycle forms, the various parameters that can be obtained are mean stress, which is indicated by the symbol sigma subscript m. It indicates the average of maximum plus the minimum stress by 2. Sigma mean. Alternating stress, or the stress amplitude, is equal to sigma maximum minus sigma minimum by 2. Range stress, which is indicated by the symbol sigma subscript small r. Range stress is equal to sigma maximum minus sigma minimum. So alternating stress can also be written as half of range stress. Then stress ratio, which is indicated by the symbol capital R, that is equal to ratio of minimum stress to that of maximum stress. Then one more important ratio in presenting the fatigue data is amplitude ratio, which is the ratio between the alternating stress, the ratio with respect to alternating stress to that of the mean stress, that is equal to 1 minus capital R, that is stress ratio, by 1 plus R. So for the case of completely reversed stress cycle, where maximum and minimum stress, the magnitudes are equal but only opposite in sign, that is one is tension, another is compression. So the mean stress is 0 because sigma maximum is equal to minus of sigma minimum. Sigma minimum is same in magnitude but of different sign. So sigma maximum minus sigma maximum, where sigma minimum is same in magnitude to that of sigma maximum, but only the sign differs. So this is equal to 0. So for the case of completely reversed stress cycle, the mean stress is 0. Then the stress ratio capital R is sigma minimum by sigma maximum, that is equal to, the ratio is equal to -1. This is for the case of completely reversed stress cycle. Reversed stress cycle. So these are the 3 forms, commonly stress cycle forms: reverse stress, repeated, and random or irregular stress cycle. And these are the important parameters: mean stress, alternating stress or stress amplitude, range stress, stress ratio, and amplitude ratio. Now we shall see how the fatigue test is conducted by means of the oldest test, that is R.R. Morey fatigue machine. So this is a schematic view of R.R. Morey rotating bending machine, where this is the specimen, this is a fatigue specimen, which is being gripped between these two housings. It is being gripped at its ends, and to which weights are attached. We have the weights, and we have the motor which rotates the specimen, and this is a counter to count the number of cycles. So initially a specimen is taken, it is fixed between the two housings, and then to which weights are attached. When this component is subjected to rotation, the upper surface of the component, it is in compression, whereas the lower surface, it is subjected to tension. So if this is a specimen, when weights are attached to this specimen, the specimen to which weights are attached, it is loaded. So this lower surface, it is subjected to tension, and upper surface is subjected to compression. So upon rotation, now this surface, when it comes to the upper surface, it is now subjected to compression, and this upper surface upon rotation, again it is subjected to tension. So like this, the same component, it is subjected to tension, compression, and this experiment, it is carried out till failure. The material is failed. So for a particular stress, whether it is either maximum stress or minimum stress or alternating stress, number of cycles to failure, it has been observed. Next, take one more sample of the same material and conduct the test at still higher value of stress. Add the loads correspondingly such that the stress is higher than the previous one, and again conduct the experiment. The sample is subjected to both compression, tension, compression, tension, and finally at some number of cycles which can be counted by means of this counter. It is a cycle counter, it counts the number of cycles. So finally we can read from this counter the number of cycles to cause failure for particular value of stress. So on, tests are conducted for a number of specimens of the same material for varying stresses. Then a plot is drawn between stress versus number of cycles to failure. Fatigue test results, they are subjected to more scatter. So tests are to be conducted on number of samples to get some meaningful results. So for number of samples, when one conducts the test, a plot of stress versus number of cycles to failure is drawn, and the plot, it somewhat look like this. So this is a plot of stress versus number of cycles to failure, which is indicated by the capital N, number of cycles to failure. And this is stress. The stress can be either maximum stress or minimum stress, or it can be alternating stress. But the value of mean stress for this type of stress cycle is 0. Why? Because maximum and minimum stresses are, they are equal in magnitude but of opposite sign. So the value of mean stress is 0. So a plot of stress versus N, capital S stands for stress and capital N for number of cycles to failure. When it is drawn for a specimen, when it is conducted for a high value of stress, when the stress is very, very high, number of cycles to failure is low. For a sample, when the stress is lowered, a slightly lower stress than this one results in somewhat larger number of cycles to failure, and so on. So finally we get a curve of this form. From this curve, it indicates that as the stress decreases, number of cycles to failure is increased. That means as the stress is lowered, the material can large number of cycles before failure. So this is the plot of stress versus number of cycles to failure, which is known as SN curve. This SN curve is also known as Wöhler curve, WOHLER, which is named after the scientist August Wöhler, who first recognized and who has done a lot of work, who has contributed more to the fatigue studies for this form of failure, fatigue failures. So this curve is also known as Wöhler curve. So as the number of stress, as the stress decreases, the number of cycles to failure increases. Some materials, they show a definite or a specific value of fatigue limit. Metals like that of materials that of mild steel and some of the titanium alloys show this type of curve, SN curve, which flattens at some specified value of stress. So this is for the case of mild steel and some titanium alloys, whereas this type of sloping curve where there is no flattening seen at specified stress levels, this is for the case of other materials, aluminum, copper, etc. So from this curve, one can define certain important parameters. So the important parameters that can be derived from the stress versus N, that is number of cycles to failure, is first is fatigue strength, which is also known as endurance limit. Fatigue strength or fatigue limit, which is also known as endurance limit. This is defined as the stress below which the material will not fail under cyclic loading, even it is exposed to infinite number of cycles. So this is mainly for the materials which show a flattening in the curve. Curve is flattened at some specified value of stress. So this is known as fatigue strength or fatigue limit, also known as endurance limit. It means that below this value of stress, for example, if this is about 375 MPa, the stress, below this value of stress, it means if the material is exposed, it is subjected to a stress of about 300 MPa, the material will not undergo fatigue failure even though it is exposed to any large number of cycles, because the curve has flattened here. So at this point of stress, there is no fatigue failure even though it is exposed to large number of cycles. So that is for the case of materials which show true fatigue strength or true endurance limit. That is defined as the stress below which the material does not undergo failure due to cyclic loading alone, even though it is subjected to or if it is exposed to large number of cycles. For the materials which do not show this endurance limit or fatigue strength, for them fatigue life is considered. That is, at some high number of cycles, for example at 10 to the power of 8 cycles, which is somewhat higher, the stress corresponding to this higher number of cycles is considered as the fatigue life. The stress corresponding to somewhat higher number of cycles, that is 10 to the power of 8 cycles, is taken as fatigue life. So corresponding to 10 to the power of 8 cycles, the stress is 200, for example. Okay, so this is the fatigue life. At higher number of cycles, at some specified number of cycles, that is at about 10 to the power of 8 or 10 to the power of 7 cycles, the specified value of stress corresponds to the fatigue life of that material. So these are the parameters that can be derived from this SN curve, which is also known as Wooler's curve. So this curve has one more importance, that is that you can see here the number of cycles to failure. I have mentioned it is from 10 power 5. So this SN curve is known as high cycle fatigue, where the cycles are greater than, where number of cycles, that is capital N, number of cycles to failure, it is greater than 10 to the power of 5. So this type of stress versus number of cycles to failure, it is known as high cycle fatigue. This is high cycle fatigue, where number of cycles to failure, it starts from 10 to the power of 5. The stresses for this type of high cycle fatigue, they are elastic. Even though the stresses are elastic, but still the material undergoes failure because small amount of plastic deformation takes place at the crack tip. Once the crack nucleates, some amount of plastic deformation takes place in localized regions. In the case of crack, some amount of plastic deformation occurs at the crack tip. So even though the stresses are elastic, the material undergoes failure at high number of cycles. So the strains in the case of high cycle fatigue is elastic, and the stresses are also in the elastic regime. Number of cycles is greater than 10 to the power of 5. And this is the curve for materials like that of mild steel, which shows a true fatigue strength or true endurance limit, and whereas other non-ferrous materials like aluminum, copper, they do not show this type of true endurance limit, and the curve slopes down. So fatigue life is defined as at some specified number of cycles, the stress that corresponds to that value of number of cycles is the fatigue life of the specimen. Fatigue strength increases as the tensile strength is increased. So the endurance limit is found to be about 0.35 to 0.6 times that of the ultimate tensile strength of that material. For most of the steels, it has been observed that endurance limit is about 0.35 to 0.6 times that of ultimate tensile strength of that material, which is found for most of the steels. And there is a correlation between the ultimate tensile strength and the fatigue strength. As the ultimate tensile strength is high for materials, the fatigue strength is also higher, or the resistance to fatigue is also higher. But this can be seen only up to a hardness of about 40 HRC. And this is not with all types of materials, because very high strength materials, they have very low fracture toughness. The fracture toughness that I have already mentioned, fracture toughness is ability of the material to resist fracture in presence of flaws. The fracture toughness, it is low, it is decreased. As the strength of the material increases, fracture toughness decreases, as well as environmental sensitivity also increases for very high strength materials. So it doesn't mean that very high strength materials can be chosen for very high fatigue resistance. this is not always, but there is a correlation that high strength materials, high ultimate tensile strength materials, they also show some better resistance to fatigue, and this is only up to the hardness values of 40 HRC. Already we have discussed about the hardness. HRC, it is Rockwell hardness 40 when tested using the C scale. C scale is a combination of the diamond indenter, diamond cone indenter, and a load of about 150 kg force. So up to this particular value of hardness, it has been found that as ultimate tensile strength is higher for the materials, the fatigue resistance is also higher. Generally, fatigue crack initiation takes place at the free surface, at the external surfaces. So once the crack nucleates at the surface, initiates at the surface, crack nucleation occurs at the surface, this crack propagates in a direction perpendicular to the principal tensile axis. Crack propagates perpendicular to the principal tensile axis and finally leads to failure. When the remaining cross section of the material becomes very low, that it is unable to withstand the load, so finally the material undergoes fracture. As we have already discussed about the mean stress, where the mean stress for the case of completely reversed bending is 0. What is the effect of mean stress on alternating stress, which is also known as stress amplitude, and the fatigue limit? As the mean stress increases, the fatigue limit decreases. It has been found out experimentally that as the mean stress increases, the fatigue limit decreases, which can be seen from this various curves. So this is with respect to stress amplitude, alternating stress, and number of cycles to failure. So this is for the case of mean stress sigma m1 for a particular value of mean stress, for a specified value of mean stress. This is for sigma m2 and sigma m3. It has been found that as mean stress increases, the fatigue limit has decreased. Sigma m3 is greater than m2 is greater than m1. Various mathematical models are there to show the effect of mean stress on alternating stress. Among the various models, the popular models or the famous models are, first we have the Goodman mathematical model, second is Gerber's parabola, and third also we have, that is Soderberg. So these are the models to explain the effect of mean stress on alternating stress. So we shall see the diagrams which shows the effect of mean stress on alternating stress. So this is a plot of alternating stress with respect to that of mean stress sigma m. For the case of Goodman, it has been found a linear relationship holds. For the case of Gerber, a parabolic relationship holds. And Soderberg model shows that this is for the case of, it is also linear, but the stress is replaced by means of yield strength instead of ultimate tensile strength sigma ys. This is for the case of Soderberg. So this is the effect of mean stress on alternating stress given by various models. The linear relationship, it is given by means of Goodman. Then this is parabolic relationship is given by Gerber's. Then Soderberg is also linear, but the replacement is yield stress instead of ultimate tensile strength. So the equation we have is alternating stress is equal to fatigue limit into 1 minus sigma m by sigma u whole to the power of x. So this is one of the important relation between the mean stress and alternating stress, where x is equal to sigma a is the alternating stress or stress amplitude, sigma e is the fatigue limit, sigma m is the mean stress, sigma u stands for ultimate tensile strength, and x is equal to 1 for that of Goodman and x is equal to 2 for Gerber's parabola. For the case of Soderberg, sigma u, it has to be replaced by, that is ultimate tensile strength is replaced by yield strength. If yield strength is used instead of ultimate tensile strength, then it gives the relationship for alternating stress and mean stress for the case of Soderberg's model. It has been found that ductile materials, the data for the ductile materials falls closer to that of Gerber's parabola, whereas for the case of notched specimens, the data falls closer to that of Goodman. It shows in good agreement for the case of notched specimens with respect to the Goodman's model. And for the case of Soderberg, we have with respect to the yield strength, not that of the ultimate tensile strength. The equation for the high cycle fatigue, it is given by Basquin for the high cycle fatigue, that is n into sigma a whole to the power of p is equal to c, where n is number of cycles to failure, sigma a is the alternating stress, and p and c, they are empirical constants. So this is for the case of high cycle fatigue, which is also known as low strain regime, because the stresses are low, they are elastic within the elastic regime, so the strains are low. High cycle low strain given by Basquin equation, that is n sigma a whole power p is equal to c. N is the number of cycles to failure, sigma a is the alternating stress or stress amplitude, p and c are empirical constants. Now we shall proceed into the cyclic stress strain behavior. This type of cyclic stress strain behavior, it is seen mainly for the components which are exposed to high temperatures. For the case of nuclear reactors, pressure vessels, heat exchangers, etc. For these components, when they are subjected to high temperatures, the stresses are of thermal origin, not of mechanical origin, because a component, it is restricted to undergo expansion and contraction. So the stresses that are developed in the component are basically from the thermal origin.